What about 5?
1, 2.
1,
2.
always data 5.
Yeah.
Okay? 2.
2. Yeah.
Actually, it's not the same IO. In case of the leaf node, it's a 3, but parent node is a 2. What if we have a huge B3 index, like the 100 depth? Sometimes, if you are lucky, 1, 2. 2 is enough. If you are not lucky, 101 IO are needed. Is it balanced? Actually, it's not purely balanced. Do you understand what I'm saying?
Yeah.
Even though we are saying this is a balance, it's a balance for only leaf node. If you consider entire node, sometimes 1, sometimes n depth. It's not purely balanced. So B3 index is still not unbalanced. It's not 100% balanced data. If that is small, it's okay. But when you have the huge indexing structure, like the 10 millions of index key, so it's different. So we need to address such a problem. How can you address that problem? So search tree problem, skew data, by changing the order, like the bottom up, we address. But in B3 index, still it's not balanced. So how can you? The problem is this one, 5 and 8, right? Why don't we move down all the data pointer to the leaf node? Okay? So that's the idea. Why don't we move down 5 to here, 8 to here? And only this one, the parent node, keep the splitter, discriminate, delimiter. Okay? It doesn't have the key pointer. Instead, it has only number 5. So less than number 5 goes to here. Equal or less than number 5 goes to children node. Then 5 will be somewhere in the leaf node. That's the idea of B plus tree. Okay, let's take a look at the details of the B plus tree with the example. Same example. This is a node structure. Before that, in this case, B plus tree, we have two types of node. One is leaf node. Leaf node structure is in case P is equal to 3. And internal node. That's it. Okay? As you can see, this is a data pointer. Data pointers are in only leaf node. Internal node does not have the data pointer. Instead, it has only key. Okay? You cannot search the data file using internal node. You need to go to the leaf node. What does that mean? So we will do the example of this one. It's the same idea as the B3 index. It's in case of full, you need to split, then promote. So first, we need to use this one, the leaf node, for first data. 8, we need to create this. It's a little bit different from the B3 index structure. Okay? I will explain this one later. So 8 is inserted and 5 is inserted. No problem. So you can search the data of 5, data of 8 using this one. Next, in case 1 is inserted, do we have a space? No, it's a full. In case of full, what? Split and promote. So, split means copy. We have 1, 5, 8. Copy this one. Same thing. Find the middle value. Which one is the middle value? 5. Okay? So, less than middle value? No. Equal or less than middle value goes to the left-hand side. That's the difference from B3 index. B3 index, keep the, we just split and promote the middle value. However, we'd like to keep all the index key value to the leaf node. Okay? So that is the reason equal or less than middle value goes to the left-hand side and the others right-hand side. A. And we will promote, but in this case we promote only the value, not key pointer, which means 5 over here. At that time we will use internal load, this one. Internal load does not have data pointer, so it will be like this. 5 will be promoted, but the 5 does not have data pointer. Instead, 5 is located in the leaf node. Then, equal or less than 5 goes to this one. This is a children pointer. Bigger than 5 goes to here. That's it. Do you understand the difference? So, let's look up the 5. How many I/O do you need to search the data 5 using this index?
1.
1, 2, 3, 1, 2, 3. Little more. Little more. No? So 3. 1. First, 5 is here. Can you find the data pointer? No, it doesn't have a data pointer. It's just a split, the data. It's just an indicator. So, equal or less than 5 goes to here. Then, you find the 5 and the pointer. This one has the pointer to the 5. Leave. Then, get the data. How many I/O? 1, 2, 3. What about 8? 8 definitely 1, 2, 3. What about 1? 1, 2, 3. Always 1, 2, 3. 1, 2, 3. It's the same number of I/O, no matter what data you have. That's the difference from B3 index. B3 index is different depending on, there's a lower bound. Okay, there is a limitation, but number of I/Os are various. However, B+3 index, always the same. Why? We move down all the data pointer to the leaf node. One more thing. This one. This pointer in the leaf node, this pointer is called sibling pointer. What is a sibling? So your brother or sister, right? It's the same node. In the same node, sibling pointer means I'd like to search data, select from student where the UV ID is bigger than 1. Okay? First, search 1. Then 5, fortunately, in the same block, so you can access. What about next? 8. You need to search again. 5 is bigger than, because this branch has only equal or less than 5. Right? So there is no way to identify this. So you need to go to 5, bigger than 5. Using this pointer, you can access the 8. Up and down, up and down. That is B3 index. To address that problem, we can put the sibling pointer. Neighborhood, this is my neighborhood. You don't have to search again. Just go to the neighbor for the next data. 5, 1, 5, then using this one, 8. in this case, it's very simple to access the data. It's called a range search. We will look at this example in the query optimizer. What is a range search? What is the equal search? So this is a sibling pointer. So B plus 3 has the sibling pointer. Don't forget to put the sibling pointer. Definitely it will be final exam. Okay. Then next, 7 is inserted. 7 is bigger than 5. So can I use this one? No, even B3 index we cannot use here. So we need to find the location. Yes, we have space. 7, 8. What about 3? 3 is less than 5. So will be inserted. Here is a full. In case of full, we need to find the middle value, then split into 2. We need to copy leaf node. And equal or less than middle value 1 and 3 go to here. Bigger than 3, 5 go to here. That's it? No. Promote only key value, middle value, not data pointer. Data pointer is here, so will be inserted over here. So 3, 1, 3, and we arrange children node.
5. I think
3, 5. 3, 5. Thank you. This one. That's it. One more thing. Pointer of sibling. Using sibling pointer, you can easily do the range search. Next. What about 12? 12 is inserted to 3, 12. Yes. Bigger than 5. We have a fortunate space over here. So can I put 12 over here? No, it's not for 12. 12 is for here. Right? However, it's a full, so we need to do split. Seven, 8, 12. Then middle value 8 will be inserted over here. Okay? Problem is, it's a full. We can follow the same procedure, split and promote. Okay? 3, 5, 8. Which one is the middle value? 5. So we can copy. We should copy the internal same node because it's kind of the clone. Okay? So it will be like this one. So 3 and 5 over here and 8. At this time, we don't need the 5 over here. The internal node will be used for what? It's the indicator, split, the value. It doesn't have to be leaf node. So in this case, it will be promote to the 5, then this one. Less than 3, equal or less than 3, bigger than 5, and bigger than 5, less than 8, and this one. So, promotion of the internal node is the same as what? B3 index. Okay? So the reason why we keep the middle value in the leaf node is we try to keep all the data pointer on the leaf node. The other internal node is only indicator, whether this is a less or the bigger, and so on. So 5 goes to here. Okay? Even we don't need sibling pointer in the internal node. Only leaf node need. That is the reason we have 2 different node types. The next, 9. What if 9 is inserted? We need to find which node will be used. Bigger than 5, bigger than 8. So we can put 9 here. What about 6? 6 is bigger than 5, less than 8, and should go to this node. 6, 7, 8. Which one is the middle value?
7.
7 is the middle value. So we need to 9, 10. 9 is 12. And copy this one. 7 and 8 goes to left hand side, and 8 goes to here. Okay? Then middle value 7 will be promoted. 7, 8. So we rearrange. Less than 7 goes to here, bigger than 7, equal or less than 8 goes to here, bigger than 8 goes to here, and less than 5, bigger than 5 goes to this node. That's it. What if 15 is inserted? Why don't you try? So why don't you try from the first full year practice? 8, 5, 1, 7, 3, 12, 9, 6. Then insert the 15 again. Using B plus 3 index. Don't forget the sibling pointer. This one. So usually solid circle means pointer. There is a pointer. This one is a null pointer. Okay? What about the real index used in the Oracle? It's a 99.99, same as this indexing structure. So exactly same. Okay? Little bit various, but the same idea. Somebody may be curious, what if the data is deleted? It's the opposite way. It's instead of split, it will be merge. Okay? So merge is a little bit complicated, more complicated than the split. Okay? But still same idea. So that is a reason from time to time your index should be recreated. The reason is that sometimes you have a bunch of the unused data, but because of the indexing node structure, you cannot use such a data. That causes waste of space, also longer time to access. So you'd better recreate the index from time to time. So that's a good idea. So when you get a job as a database programmer, but my query is correct, I believe, but it's running very, very slow. At that time, you can ask your database administrator, why don't you recreate the index? Okay? Then you will get the faster response because of the nature of the B-tree index. Okay, let's solve the problem together. 15 is bigger than 5 and bigger than 8, so definitely goes to this one, but no more space. So we need to split into 2. So 9, 12, 15 is a middle value. So middle value will be promoted and still exists in the left node with the data pointer. It's a 12. So we need to split. So 7, 8, 12. Which one is the middle value? 8. So less than 8 goes to left hand side because 8 goes to right hand side. 8 will be promoted. Then we arrange bigger than 5. Less than 8 goes to here, bigger than 8 goes to here. This time, bigger than 8 less than 12 goes to here, bigger than 12 goes to here, then sibling point. And like that. But last one. How many I/O do you need to access the data? 1. In this case, how many I/O? Total I/O? 4. What about 6? 4. What about 7? 4. What about, no matter what data I call, it's a 4. Always 4. That means query optimizer can easily decide it will take 4 I/O. Okay? It will take exactly 1.5 hours to go to Manhattan. Then you can believe the train instead of the driving. Driving, there are a lot of conditions. But train is always 1.5 hours. Same thing. It will take 4 I/O. Professor Lee mentioned only I/O for the time. Yes, that's true. That is the most expensive, the resource to access a hard disk drive. So it's the same as seek time. I think operating system you learn this one. Okay? No? Why don't you take a look at your operating system textbook? Physical I/O is the most expensive, the resource. So we will use the number of I/O for the time. Okay? So it will guarantee, it will take only 4 I/O to access the data using this one. That is the reason B plus 3 index provides perfect, the balanced index tree. Okay, so we will continue next class regarding to the advanced topics in the database design as well as the database tuning part. Thank you. And